Hello and welcome to this tutorial. Today I'll be covering the terrain script, colorization script that I've written, and that's to promote kind of an understanding of exactly what the script is doing and how you would be able to interface, change parameters in the script alongside making modifications potentially to it and in terms of your own customized colorization routine. So go ahead and get started here in terms of asking the question of what is terrain colorization and what is a terrain height map. So terrain colorization, if you have any familiarity with looking at like a topographic map, you may have seen contours on a given map, given by, say, something like contours or isobars or something which indicates elevation, different elevation ranges, and then alongside the map might have been colorized to the degree that the lower elevations have perhaps some sort of whiter or lighter color texture relative to higher elevations going greener and greener, darker green, and then potentially even getting up into red areas, or actually I should say for lower elevations that are going below a specific stage, getting into red colorization routine. So it kind of gives you a sense of scale, depth scale between the highest and lowest points on a given map. Terrain colorization actually can go a little bit further in terms of like artistic rendering, to the extent that you can actually procedurally model a level of realism that isn't found typically in just the simpler of terrain colorization routines, but actually resemble something that you might see in a photorealistic kind of context. So they can be also quite sophisticated, and I've seen some terrain simulation models, or modelers I should say, that have provided some pretty photorealistic types of terrain surfaces, and they do these fairly rapidly in terms of rasterization. So it is something that is nice in the context that you don't need to have an artist necessarily come in and do the depiction, painting the color in, or rendering the their own artistic version of what's occurring there. But if you provide the types of parameters, and given the level of sophistication and the routine, you can provide or obtain pretty amazing colorization routine or colorization maps themselves. So something to keep in mind. Moving on to the next question, and that is, what is a terrain height map? It kind of pertains to the first question, which is we know that if colorization is given where a particular point in the map is colored green, then we know there's some sort of height value associated with that. So that height value is actually part of a height map. So when we go pixel by pixel on a terrain height map, and I'll show in this next slide here, which is actually the Yosemite region, although you might not know it just looking at it directly. But on this given height map, we can see that there are grayscale pixels throughout the map in varying degrees, where the lower elevations are represented by the darker portions of the map, and the higher elevation regions are represented in the lighter portions of the given map. So we look at this, and typically in a height map routine, or translating the height map to a terrain mesh, we would go pixel by pixel on the height map, gathering its grayscale value. Now, normally these grayscale values might be either in like an 8-bit or 16-bit grayscale format. 8-bit format would indicate 255 different possible height scale or height variations, while the 16-bit would be 256 squared number of variant height positions. Most height maps, if they're worth their salt, worth their grain, I should say, they would likely be a 16-bit format, because you have, well, you can imagine 256 squared variations of height elevation, which provides a lot more smoothness in terms of conveying a given landscape relative to kind of 255 step variations alone. Of course, you could use potentially, and I've done this before, 8 bits per channel independently, and describing the grayscale variations where the red, green, blue channels are all kind of their own independent grayscale height variations, but they're used in kind of articulating kind of a whole different routine, kind of numerical routine, and describing all the possible variations. So you can actually get into, I think it's something like 24 bits if you use the RGB independent channels, as opposed to keeping them kind of grayscale unified. So that's kind of one thing to keep in mind. But anyways, returning back to the map itself, we can see kind of in this area here, there's El Capitan, and then the valley described in this kind of darker region, Yosemite Valley, given throughout this dark region. So in the next slide here, I'm showing the actual terrain colorization, and that indicates the flood stage areas, or the low elevation point areas, given in blue. Darker blue indicates the deeper elevation flood stage elevation points, while we get into green, yellow, and then potentially red and white variations, which are all inevitably indicating higher elevation points relative to one another for those different types of color variations. So this kind of all leads into the particular problem in the script, which is when we are dealing with a given terrain landscape and or a mesh, we're actually dealing with and colorizing the terrain. We have the mesh, so we're not actually needing to work with a height map, but we do need to obtain one. But we wouldn't be necessarily working unless we had the height map file associated with the terrain. We might not have the height map values, but we certainly would go about the process of obtaining that, because we do need to colorize the terrain by somehow knowing the height positions on that given mesh. So this does lead to another problem, which is that the mesh itself may not one-to-one correspond for each point on that mesh. Each vertex on that mesh and defining it may not correspond one-to-one to the map, the color map that we want to build for it, the height map, or color map. So the height map that we might collect, let's say we had a mesh, terrain mesh, like an ant landscape in Blender, might generate a mesh with 60 vertices by 60 vertices, or 60 lengthwise by 60 widthwise, and we would have something like 3,600 vertices, height map vertices. But if we wanted to build a picture of that color map, that terrain. We might want to build a picture that's much bigger than that particular height map. And, we might be working with the picture that's maybe 1,024 pixels by 1,024 pixels. So we have 1,024 pixels squared point positions that we need to know the height map positions relative to a map that we only have 3,600 vertices or height map positions. So we have a kind of a translation problem that's occurring right there in the context that we don't have enough points to create the type of color map that we want to create. Well, the picture on the left in this diagram here, and the question that's immediately asked is, what is the point of bilinear interpolation? That actually leads into the problem that I've described here, which is if we didn't bilinearly interpolate going from one map to the next that we wanted to create, we might have something like the diagram or the picture shown on the left here, where we chose for each vertex, each group of vertex that would consist of a face, and that would be like 4 height map positions. We would instead choose to move all of the height map positions to one particular level represented on that face, one height position. And so maybe that might be the most maximum height position for all 4 vertices. We would choose the maximum height position for all of those and represent that face at that given height level. To describe all the points kind of in between that we needed to fill in for the given details as we're expanding our rescaling our data to make it fit into the other color map routine that we wanted to build. Because remember, we originally were working with only 3,600 height map positions, but we actually really need something like 1,024 squared position. So for each vertex, as we've rescaled it, those positions, we determine we need so many positions in between to fill in the detail on that color map. We're building these kind of squares and cubes, and then we end up with something like this Minecraft world depiction that's shown here. But relative to the terrain mesh that we had, it didn't really look this way in terms of the height map. So it looks kind of very boxy and not very continuous. It has a lot of step discontinuities shown in the map. So this leads into another point, which is it actually leads to the answer of what is the point of bilinear interpolation. Bilinear interpolation is kind of shown by example in the diagram to the right here. If we take 4 vertices or height map positions on a given face, and the face is delineated by this square or kind of a rectangle, if you will, those 4 positions in between them, we have all sorts of points. Well, we can actually mathematically extrapolate what those points in between would look like on the face. And what happens mathematically when we do bilinear interpolation is that we fill in the data, those in between points on the mesh, and determine what they would look like. And subsequently, we get away from this very boxy looking interpretation of the position values between those 4 vertices, and instead get something that's very continuous and smooth in between. So that's basically what bilinear interpolation is accomplishing. The bilinear portion of this, when we say bi, what we mean is that we're working in 2 dimensions to do the interpolation. So we're taking into account 2 sets of vertices on their respective x-axis when we're interpolating, and then we're interpolating in turn for 2 sets or 2 vertices two sets of vertices on the y-axis and determining that given position, desired position that we're looking for, XY position, somewhere between the four vertex coordinates that are shown. So that kind of answers that question and kind of gives you a sense of what's going on when we're doing in the main script, when we're having to resolve around a particular problem, which is creating enough data to fill in the color map that we want to do that resembles the old system. And by the way, with bilinear interpolation, if you understand that, you've also understood something of the process that occurs when like your Adobe Photoshop or any sort of photo program, when you rescale or resize the photo, they will usually have to fill in again the data points, missing data points that would occur in rescaling. So, or truncate in some cases. But for instance, if you're going from a smaller to larger photo, you're going to have a lot more RGB pixel coordinates under the new resized photo that's much larger relative to the old photo. So what they'll do is have either bilinear or bicubic interpolation process in the resizing, or they have, I think, other mathematical operations that can be performed in resizing the photograph. So if you kind of understand what bilinear interpolation is doing in this context, you'll also understand what's going on when you're trying to resize and rescale data points. When you've got a set of data points, it actually goes beyond just the application of building terrain color maps, but works in many different fields and disciplines. So it's a really cool area of mathematics to understand, and I highly recommend, for instance, potentially going to like a wiki website and reading up further on it to understand kind of mathematically what's going on. I'm not going to delve into the exact geometry of it, but in essence it is pretty, once you understand the basics of interpolation, it's pretty easy to understand. So I'll go ahead and move on to our terrain colorization script itself, and I'd like to go ahead and cover the parameters, the main parameters that are user adjustable. And then I'll go ahead and get into kind of some of the nuts and bolts of the program itself. So with the colorized terrain, starting at the very top of the program, and I presume that our listener may have some sort of Python programming experience. If you don't, I can just kind of briefly summarize at the very top of the program when we have these import or from, like math utils import star, or a global demx, demy, normfac. These are kind of like preliminary declarations, things that we would use later in the program. They're oftentimes, like in the case of the import and from something import star, what that indicates is that we're importing a module that we're accessing, specific functions or classes that would be used later in the program. So that's kind of the purpose of that. Math, like import math, that's typically associated with a import or we might use a math cosine function, or like import random would be given to using like an import or using a random function and generating pseudo-random numbers. And then we have the from mathutils.noise or import star, and that's simply importing. That's actually a Blender utilities, the math utilities, but it's also nice because Blender provides the math utils noise, which is a fractal noise generator, or actually different fractal noise functions that you can call for generating fractal noise, which is actually used in this program for terrain texturing. So moving down to the actual variables, we have this bicubic is false. I've actually commented don't make true enabled at the moment, since I haven't completed the bicubic interpolation portion of the script. So you'll definitely want to keep that variable as is. But we do have this dim_x, dim_y, which is actually the dimensions, scale dimensions of the color terrain height or color map that we wish to produce. So in this case, it's stated 1024. We have equal size on both the width and the length, or the X and the Y axis, dimension axis there. And then we have going below that, it looks like land low, going all the way down to dark grass. They have the same type of tuple, their tuple parameter. And when I say tuple, it's a three tuple, which means there are three different values given. These are actually color tuples. So that when I say color, that means they're in 8-bit format, 8-bit per channel RGB format. So within 8-bit format, as I described earlier, we would have 256 different variations of number, and they're integer based. So the numbers range from 0 to 255. So if we put in any one of these color tuples a number from 0 to 255, that certainly would be accepted by the compiler or the interpreter, Python's interpreter, when it's running the script. If you're not familiar with the RGB format, you can use any sort of Photoshop editor, or you can go online to like a color picker palette, and they will provide you for a given color that you pick on in the palette. They'll provide you with an RGB format of that color that you picked. So the descriptions here are given for each of the particular color parameters. So if you wanted to insert some sort of color that was associated with the land pixel, we have the description like land low, land high, land low rock, land high rock. These are all given in a way so that you kind of know where it's being applied on the map for the given height map range. So if you're wanting to color in certain ways and the land base textures are within a specific range, hopefully your program will have it delineated so that you know where that color is likely to be applied as it's being applied on the height computation there. So going down a little bit further here, I'll actually go ahead and skip beyond the colors, but that does, all of those are modifiable, user modifiable. I mean, you can adjust them however you like. And getting down a little bit further, we actually get into the fractal noising parameters. So we have the fractal noising parameters given by n-size and basis. And then it would actually go down a little bit further to some of these other variables like lacunarity, depth, and dimension. So those are all part of the fractal noising, like random fractal noising. So if you wanted to control kind of the fractal noising aspects, you would do so with these parameters. Now the two of them are not stated exactly what they're applying to. That's the n-size, for instance, n-size and n-size 2. The n-size actually applies to a land fractal noising between like a land grass pixel and land dirt pixel. So that N size, if you have any familiarity in Blender with like the cloud texture, you can adjust the size parameter of the cloud that changes the magnification level, either demagnifying or magnifying further a given level of the cloud. It gives you a sense of, by adjusting the N size parameter, how you can demagnify or magnifying the effect of the fractal noising. So with the large number, it actually kind of zooms in on the cloud, and with the smaller number, you have kind of a more removed effect. So it'd be like you, the observer, being much further away, observing these group of cloud clusters. So the in size, I believe it ranges from 0.01 to up to like 10,000 in terms of its min-max range. And then we have below that, it's N basis, N basis 2, N basis 3. Those are actually the noising basis. So you can like select between Blender original noising basis, or you can go to Perlin, New Perlin, or you can go to a Voronoi basis. So if you know anything about these different types of fractal techniques, gradient noising techniques, you'll know what the N basis, what it represents. So like gradient noising, it alone, it doesn't produce perhaps the type of fractal texture or that we may commonly think associated with the clouds. That actually comes through what's called a fractional Brownian motion, which is kind of a frequency summation of the gradient noises that at different like coordinate positions, and they're all kind of summed up. That's using again fractional Brownian motion technique to produce that. So the N basis actually applies to not the fractional Brownian part of it. It doesn't actually produce the noise, the actual noise value, but the N basis does cover that. So if you're wanting to choose like an Voronoi basis, it would be set to 3. Default is usually the Blender, which is kind of like a Perlin variant. Blender, the Blender version is. And I have that also notated a little bit further down, I believe, in terms of the possible options. Yeah, there's Perlin, New Perlin, Voronoi, F2, F3, F4, F2, F1, Crackle, and then Cell Noise. So there's like up to 9 different basis, or 10 different basis variant types that you can work with. So it provides quite a bit of flexibility in terms of change and adjustment in terms of the noising procedure. So just below this, we have it's a CF hash map, or dictionary as it's called in Python. This is actually a coefficients function table that I drew up. It's used for cubic fall-off functions, polynomials. So the basis, the range basis that we work with these fall-off functions typically run up starting from 0 on the XY axis, and then they go like up to 1, 1, or in some cases they'll go to these key fall-off points like 0.05 to 1, or 0.05, 1, 0.1 on the x-axis and 1 on the y-axis, 0.2 on the x-axis, 1 on the y-axis. So I've used these different fall-off functions for the sake of feathering techniques like color mixing feathering techniques to delineate or to smooth out the differences between the cutoff variations in color. So it's a little smoother in transitioning, say, from a flood pixel to a land pixel, or it's a little more color smooth in transitioning from a land, grass, dirt pixel to a rock pixel on a higher gradient slope. So that's how those cubic functions are being used. And the CFK1 and CFK2 variables shown below that hash map is actually where we refer to the cubic fall off, one of the cubic fall off keys. So that it does technically need to match. We couldn't just choose at the moment unless you defined a larger table that had the value that you were looking for in mind. We would be restricted to one of these key values. That's 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. So the CFK1 and CFK2 parameters can take any one of those values that are shown there. And scrolling down a little bit further and returning back to the fractal noising parameters, we have lacunarity. If you have any familiarity with that, and Blender, you can use lacunarity under the ant landscape generator. So with that, if we just see lacunarity, it will change necessarily the smoothness and the degree of texture noising that is kind of the fractal texture noising. So the lower the value means that I believe it means that we return to something of the original gradient noise procedure or gradient noise value prior to fractional the Brownian motion series summation. So it would, I believe, get closer to the actual original gradient noise for one position value relative to lacunarity being set at 2 by default, where we get much more of the motion fractional Brownian motion effect in terms of the series summation, in terms of the mathematics of that. So usually I've seen people suggest ranges 1.7 up to a little bit higher than 2. The default is typically set around 2. Going below that, we have the depth parameter, and depth gives you kind of a finer degree of resolution in the texture. So like with the clouds, if you want to see a little more finer detail, you would set the depth higher. And so you can change that from a minimum of 1 to a maximum of 16. The default's set at 6. So it's described as the fractional Brownian motion frequencies. This is the frequency of the fractalizing characteristic. It's kind of its accurate description there. Then we have dimension. That one I don't really mess around with as much. Typically by default it's set to 1. It's kind of like the depth parameter and the lacunarity, kind of a mix between the two. I've kind of associated this with covering the possible roughness or smoothness in rendering noising a given map. So that's again default set to 1 normally. And that covers some of the main user input variables. We only have 2 more that I'll cover a little bit later. The rest of the program, prior to getting into kind of the preliminary kind of nuts and bolts computation work in the program, the rest of the program itself is defined with declarations of functions, utility functions that we would be using in the later in the program. So these functions are always I always declare them before I actually get into kind of the basis of programming work that's to come later there. So going down a little bit further, we'll actually get into the area of kind of preliminary processing work. And as I described earlier in the beginning of this little segment and describing what is bilinear interpolation, this is exactly where we get into doing some of that type of work leading up to it and into it before we actually get into terrain colorization. That'll be covered after that. So we have this scene object as SCN. It's bpy.context.scene. This is just a variable that's referring to the Blender scene context. This is how we get our terrain object mesh data. So the landscape's assumed selected, so we take the active object in the Blender scene. Then we set the object to edit mode, which is kind of interesting because apparently in Blender we can only access the mesh data, the bmesh data, when we're in edit mode, so it's kind of important to have it set. So we automatically do that whether you have the object selected and you're in edit mode or not. It automatically does it with the script. And then we go ahead and grab the object data, which is under that bm variable bmesh from edit mesh, and then in the parentheses object data. And then it looks like we have below that some additional declarations: the Heightmap 2, normal map, pix Heightmap, and some couple other variables there. And then we have some more variables, setting some parameters here. Those are not user adjustable, those are computation. As it turns out, like the scale fx fy is actually overridden a little bit later. I think initially when I was approaching this program, I never pulled this out, and I was thinking of solving the problem under rescaling in one way, and I decided that I wanted a different way to do it. So we can ignore those two. Then we get into some other declarations. You may notice this kind of -1 times float, and then in parentheses inf, that stands for negative infinity. So if you ever need to declare something as infinitely large number, this is how you do it. With all of these are kind of purposeful in the context of minimum and maximum. And the reason why I say that is that if you arbitrarily initialized a number, say, to what you thought were a minimum, it may not be generalized in the applicable sense to all possible minimum values. In other words, what I think is a minimum may actually in reality be not a minimum or not likely to be overridden, in the context of another minimum that comes along. So being able to initialize your parameters to a minimum or maximum that's kind of in the absolute sense is important, or the alternate strategy is to set your minimum like to the first array element in a given series, or first list element, like in Python, for comparative sequencing when finding minimums and maximums. So that's what we exactly do here as we start referencing the vertex data. That's under the for loop, for v and bm verts. The v is just the reference to, it's an object reference to in the bm verts when we're iterating through each verts container. So then we access the coordinate data, that's the v dot CO, and that's broken up into its X, Y, Z, or as we've referred to the variable H, which is the height map H height value. Then we have the normals. If you're familiar with the normals, you probably don't need an explanation, but kind of the simpler explanation, if you did need it, is normal is kind of the change of the slope with respect to like all other position values, how that slope is changing, or how that particular position is changing with respect to all other points. So we want a sense of what the gradient, what the slope of the of that particular face is. We would grab the normal data. So any normal that's pointing straight up, the vector is just pointing straight out of the plane, straight up and out, indicates a flat area that's flat. And then you can imagine pointing perpendicular to a very steep mountain, almost vertical mountain, would point perpendicular outward. So it would actually appear horizontal, say to a plane, a flat plane on the XY axis. So that kind of gives you a sense of what gradient vectors are like. They always point perpendicular to the slope of the face at that particular point that they're being measured. So we go about commencing this loop, going through all the vertexes, commence finding the highest and the lowest position points. We also find the highest, the largest X and Y coordinate values, and the smallest X and Y coordinate values, where it is assumed that the terrain mesh is in some sort of rectilinear, given in some sort of rectilinear coordinate fashion, or rectangular fashion, square or rectangular, either way. So this is all kind of important because with the measuring the minimum and maximum X, minimum, maximum Y, we need to determine how to scale the terrain mesh relative to the color map that we want to build, which is 1024 in this case, squared, pixels squared. So it's dimension X is 1024 divided by the distance between the minimum X and the maximum X. So that gives us a sense of scaling between the scale ratio between the terrain mesh and the color map that we want to put together. We do the same thing for scaling on the y-axis. Then below that we have this what's called TRF variable. Now, if you've ever dealt with the problem of scaling any sort of object in Blender, you may notice that, I don't know if you've ever picked a different point of origin and scaling an object and seen the effect of scaling it. But if, for instance, you chose a different point of origin than like the center of a cube, you might have the cube expanding outwards in a way that looked a little bit different. Or if you had a circle that wasn't where we weren't expanding outward from the center of the circle, some points on the circle might expand out with greater acceleration relative to other points. This is kind of like the what is that terminology that I've heard with I was thinking of the inflationary universe or something like that, with the raisins in a pudding or something like that, and you're baking it in the oven, and it could be possible that all points are expanding at the same rate, but it also could be possible that we have non-homogeneous acceleration where some points are accelerating and at different rates relative to the others. Well, we kind of deal with a similar problem. I hope my explanation was sufficient there, but we kind of deal with a similar problem where when we scale an object, we want to ensure that the geometry remains invariant insofar as like their scale relationship properties. In other words, if we're scaling on the x and the y, the geometry is going to look invariant. It's going to have the same sort of general shape, look about the same. In other words, we might not be able to tell the difference between the two if we had no sort of scaling metric or metric distance, a ruler that told us that one object was larger than the other. If we rescaled it and changed our perspective distance, we might not know that we actually scaled that object. So we want to ensure that we do that when we're scaling here the data. We want to ensure that its geometry remains the same. So we want to translate the point of origin so that it's given at the point where we're not going to affect the general geometry, and that scaling is going to leave it invariant in terms of its overall shape. So all we're doing is just changing the coordinate point, the minimum coordinate point and the maximum coordinate point, so that it conforms to the new desired color map positions, boundary positions, I should say. So we have to translate the point of origin, which is what we do with that TRF double list, and it's a two-value list. And then we have that SCF, which is a scale factor, XY scale factor. And then we take the difference of the maximum minimum norm, which is the difference in the gradient slopes of the map. And then going down a little bit further, I have a conditional. Where I've got this all caps norm 0 and then norm 1. It is basically the designation that indicates whether the norms are facing out or in. In Blender, you may have run into the circumstance where your norms are facing out, and that affects the texturing properties in terms of shading. So like if some of the norms are facing out, some norms are facing in, you're going to have some kind of odd shading problems that may happen. And so you found out that maybe you had to conform all the norms so that they were uniformly facing out or uniformly facing inward to ensure that the gradient or the texturing light shading was all consistent going from face to face. So we actually measure that from vertex to vertex to make sure that that they're either or. Actually, the script doesn't change or modify in the case of mixed norms. I would leave it up to the user to and knowing that from the mesh. And usually you can see that on your mesh because you'll be given kind of some strange, odd little shading artifacts that start to show up when you go to like a rendered shading mode where you can kind of clearly see it. And you can modify that in Blender, going to edit mode and then changing the norms of the individual faces or vertices so that they're all given to a specific direction. I don't have anything that code-wise goes through and handles that automatically, but I imagine it's not very hard to program that if you ever wanted to handle that from a procedural standpoint. The script doesn't really handle that part, though. Moving down a little bit further, and we have the norm cutoff. That's also the norm cutoff is how, and if you remember where I said earlier, or maybe I didn't, where we talked about applying like a rock texture to some land pixels, where the gradients are sufficiently steep, where we have steep slopes, then we can apply gradient rock texture to those particular areas. So in describing those areas, we might want to establish some sort of norm cutoff. In other words, that it's sufficiently steep enough to say, okay, well, this should be rock, not grass and dirt. So we would apply that using a norm cutoff, and we go ahead and define that here, and that's given also under the C-scale parameter, which indicates the cutoff, the gradient cutoff variation relative to the minimum maximum norm, or minimum or maximum norm. So you're wondering why we have the minimum norm in one case and the maximum norm in the other. Is that the minimum norm in the case of negative norm values is actually the number that's greater than the maximum norm. And so when we're applying that, well, actually take that back. The minimum norm is the smallest possible number, and it -1, when the norms are all flipped out, is flat. It's just pointing downward as opposed to pointing straight up. It's pointing in the opposite direction, down. So if we had a minimum norm set at -1, we would be applying based on the difference between the minimum and maximum norm, the C-scale would cut off, which is 0.1 times the norm difference. So if we had the maximum norm at -0.5, then we would have a norm difference of 0.5. And so 0.1 times 0.5 would be like 0.05, I believe. 0.05 added to -1, which would be like -9.5. That indicates the cutoff of when we would start applying the rock texture for any sort of land pixel. So that and we do it in the opposite direction if we have all outward or upward facing norms, where the max norm is likely given by a vector pointing straight up, and then we're subtracting from that to find a given cutoff where we have little steeper slopes. So if the norm's pointing straight up, it's on flat ground, and if it's pointing slightly askew from that, again, something like 1 minus 0.5 would be a norm difference of 0.5. So 0.05, which would be 0.95 for the norm cutoff on the positives. So anything less than 0.95 would have a rock texture applied to a land pixel, or a land determined pixel. So that's that norm cutoff variable is kind of important there to pay attention to. That's how you establish, for instance, applying a given texture for a certain type of like gradient norm range. You can set this. I haven't actually set it up for bracketing, but I imagine you could easily incorporate like brackets of norms so that you have steeper terrain and successively different types of textures for steeper and steeper terrain in all of that differencing. So it's kind of something cool to keep in mind, that when you're setting this up all up, it's not based on absolutes. The cutoffs are not, they're all based on like, ratios relative to like the total differences given between the maximum and minimum gradients on a given slope. So you can have rocks showing up on even like subtler, kind of rolling, undulating hills, or even on seemingly very flat terrain, if you wanted to do that. So, I mean, that's how the script is presently set up. In any event, we go down a little bit further, and we have this diff variable, which is the maximum, it's a measure between the maximum minimum height, and then we have the flood, and then mountain, that's floodplain and mountain levels. So that's based on the difference in the minimum maximum height. So if we had like from the actual difference, like terrain mesh difference given like from 0 to 10,000, then the mountain stage would be set at any pixel above, say, 5,000 in this case. Since we're working at the mountain stage at 0.5, it'd be 0.5 times the difference, which is 10,000. So 5,000 sets the, and by example, 5,000 would be the cutoff range for a mountain-based pixel. And conversely, with the floodplain, from 0 to 10,000, we would have, looks like 100, any pixel below the level of 100 would be set up as a floodplain pixel, meaning it would be a blue, likely water blue colorization, somewhere in that range. So going down a little bit further, I'll skip past some of these initializations here, the land map and land map prev. Then we got the land map 0, 1, 1. Those are, I believe, generally unused, at least for the body. They're not really needed to know what's going on there in this script. And going down a little bit further, though, we start to get into the actual bilinear interpolation portion of the data processing. So if you remember what we described with bilinear interpolation before, we're actually rescaling the data and then filling in kind of those data points that are in between that data itself. So we actually access the vertices on a per face basis when we're accessing the terrain mesh. We then take those vertices and we'll determine their ordering so that we can apply it to the bilinear interpolation routine. And excuse me there. So by ordering, what that means is that we know what the minimum and maximum pixel in terms of its XY value is. And we sort the set of those pixels, kind of important before we go to the bilinear interpolator, when we do all of that. And we do, I believe, the same with the also collecting the norm vector. Well, it's a z norm z value, something like that. But that's also added in. And so we go down a little bit further, and we actually get into where there's an explicit call given under this H equals bilinear interpolation. That's where we're actually saying, okay, well, we know that there's so many pixels between on this given face. When we're rescaling this data, we know we're going to have so many pixels that we need. We've determined that based on computing that all prior, determining exactly how many pixels we need to collect, and then we go ahead and loop through all of those different necessary pixels to determine what their given height, corresponding height value is. And we do the same with the normals to determine what from, again, the missing data that we need to fill in the gaps with, that we're filling in all that information there. So that's something that is quite necessary, because once we go ahead and get into the terrain colorization, we'll actually go pixel by pixel on the dimension X and dimension Y going pixel by pixel and colorizing. So we need to have all that data set up and ready to go. So this area right in here is again covering kind of that preliminary processing work and building up the necessary height map that translates to the desired scale regions that we're looking for in the color map that we're wanting to build. So kind of getting down now to the nuts and bolts of the program, and that's colorizing routine. We go through the actual kind of per pixel by per pixel colorization routine, and we'll notice that's for J in range dim Y, for I in range dim X, that's going from 0 to 1024 for the J, and for I, that's going from I is equal to 0 up to 1024. So if you're familiar with C++ or Java, it's just like with the for iterator starting int I equals 0, I less than dim X, and then, for instance, semicolon I plus plus for an increment operator. It's kind of simplified in Python for making setting that loop in terms of its kind of written language. And then we kind of put in a couple of conditionals here. If I, J not in normal map, we skip the computation. We neglect it, and because we obviously don't have the data to fill in, which is not necessarily a problem because my bitmap interpreter script also takes into account the possibility of missing data and just kind of fills in a pixel, arbitrary pixel. And hopefully that doesn't happen because you might have something that's kind of sticking out like a sore thumb. But in any event, I did leave or account for the possibility that maybe our normal map or Heightmap didn't collect something that it needed to, that it might have needed to, but it doesn't necessarily have to have it. So we go down a little bit further. We have we get the Heightmap data for the IJ coordinates that are shown in that given Heightmap, and then we decide whether it's a flood pixel, or whether it's going to be a mountain pixel, or whether it's going to be a land pixel. That's given by these three different conditional statements. If H is less than flood, or elif, or which is else if H is greater than mount, and then else, which is a land pixel option. So three different types of height stages we can decide from in terms of color, or engaging in our color mixing routines. Then, and I'll just go ahead and cover the flood portion of what's going on here. We run to, this is a fractal noise variable, n chords 3, just takes the n size 3, which is this is flood stage fractal noising, and we apply the necessary kind of preliminary work. And by the way, I got this particular script idea. It was actually came from the landscape generator directly. So if you're wondering why I'm applying this formulation, it was actually not mine originally. It was came directly from the Ant landscape generator and generating like fractal noising. So this is how you would do it, or how you go about using like the n size parameter and applying that. And you remember what I described in size before. That's like the magnification or demagnification of the fractal noise itself. This is how you would do it. So that generates the fractal noise a fractal noise value with that call below. G-val 6 equals fractal n-chord 3, dimension 3, lacunarity 3, depth 3, and then basis 3. With the fractal noise, something to keep in mind that the scale range that it works from is like -1 to 1 usually. In some cases, it does go outside that range. But mostly, I've always thought of it as being restricted to -1 to 1. I did leave the contingency that it may not fall within that range, and so I had to apply a clamping that's shown below to ensure that we restrict the value so that it stays, either no greater than 0 or no greater than 1. No less than 0, no greater than 1. So, but prior to that, we also do that's taking into account that the possibility that its range is normally where we might expect it, which is -1 to 1. That we rescale the values so that they fit between 0 and 1. So to do that, I shifted the minimum value so that its maximum, or that the minimum is reading at the point of origin 0 and not -1, and that the maximum possible value, if we shifted it everything from -1 to 0 and 1 to 2, 1 plus 1 is 2, so the maximum value would be 2. If we multiply everything by 0.5, the maximum value would be restricted to 1. The minimum value is still 0 because 0 times 0.5 is 0. And everything in between is going to be between 0 and 1. So that's how we rescale the fractal noises, of the fractal noise values, to ensure that they're on that restricted range of 0 to 1. You might ask, well, why do we want to do that? Well, as it turns out, with linear interpolation, we want to have our restricted range from 0 to 1. If you know anything about linear interpolation and the mathematical formulation on that, we have one parameter that is like W and multiplied times like the color, and then we have another parameter which is 1 minus W, which is multiplied by the other color, the companion color. So 1 minus the maximum of 1 would be 0, while 1 for the other multiplied times the other color would stay at 1. So we don't have the possibility of that parameter producing a negative number, a negative like multiplied number in there, which could possibly produce a negative value if we didn't have something that was negative. And secondly, where it's exceeding like 1, which is the maximum possible value of that parameter. So whenever you do any sort of linear interpolation, whatever ratio, mathematical ratio that you set up, you always want to make sure that the range is restricted from 0 to 1, whatever you're doing. So to do that, all you need to keep in mind is that you just rescale the data, translate, and then rescale it. So when I say translate, you're just simply moving the point of origin to the minimum possible value that you want to set at 0, and then you're multiplying to rescale it. You're multiplying, which would be the maximum value minus the minimum value, that all divided by its ratio H max minus H min for whatever ratio max value that it possibly has. So it's something to keep in mind when you're setting up some of the mathematics on these like color mixing interpolation routines. So we go down a little bit further. We actually, when it says lerp color, that's where we actually do the color mixing. In this case, we're using G-val 6, which is just the gradient fractal noise to do it. So it's going to be producing with those colors, like the blue colors, different variations of blue. It's going to be producing like kind of that almost kind of cloud, but it's with the Voronoi basis. So kind of like a rippling water kind of effect, kind of texture effect. And we do that for kind of the low water positions and the high water positions, kind of similarly. And then we do a height interpolation, height relative to flood stage interpolation, in deciding, whether we're using the low or the high gradient color value. And then we go on a little bit further down below that. That's with the lerp color, water low, water high. We also use the gradient noise, and we interpolate that with the gradient value. And then we interpolate between those. So we have, in essence, like 1, 2, 3, 4, 5 different chained color mixers that are going on here in this kind of the determining the color pixel for the flood stage pixel. So going down below that, I'm going to skip through the mountain section since I've kind of explained the basis of what's going on with the color interpolation, but I did want to cover, and I'm going to skip through on the land pixel, this N chords 2, since I've already kind of explained that. In the water section, it's the exact same that's going on in determining the land pixels. One does apply to land to grass dirt texturing, and the other N chords 2 applies to determining like a kind of a rock fractal texture. So we're using the N chords for, again, the grass dirt, and the N chords 2 is going to the rock fractal on the land pixels. So going down a little bit further, I'm going to skip through the rescaling of that gradient noise since I already explained it's the exact same that's going on there. I'll cover where exactly and how we implement rock texturing. So if you remember earlier where I described this norm cutoff, the computation, the norm cutoff is determining where, okay, our slope is sufficiently steep enough where we want it. We do a test to see that that's the case. In this case, we use the z variable, which is corresponds to the norm z, that tells us the steepness of that. We see that it's sufficiently, the slope is sufficiently steep enough, then we go ahead and apply the rock texture. The actual rock texturing procedure is the same in terms of color mixing that we had done with any sort of fractal noising before. We used, in this case, Voronoi, and we just happened to use rock texture colors as opposed to the blue for the water. In this case, we also can change the size, although I don't know if I did it in this particular case, had a different size, but we can also change the scale size of that noising procedure to produce kind of like a different, a look of the rock, in terms of its noising, scaled noising relative, say, something like the water or anything else that's being gradient noised, or gradient and then FBM noised. So that, again, it's kind of something important to pay attention to, this test C, testing whether slope's sufficiently steep enough. The other thing that to pay attention to in the script is the feathering of this rock texture relative to a land pixel. So that's occurring here with this test where it states if RNC diff greater than CFK1, then this, we just set it to the regular rock texture. Otherwise, if it's below that CFK1 value, which is something like, I think, 0.1 or 0.3, and then we go ahead and we determine where, using that cubic function, if you remember that cubic function hash map that I described earlier, That's for cubic function fall-offs going, say, from, in this case, 0 to 0.3 on the x-axis. We'd be going from 0 to 0.3 on the x-axis to 0 on the y-axis up to 1. So at the maximum possible value would be like 0.3 on the point, or the coordinate position 0.31. So it's kind of important, because if our gradient slope value is sufficiently close to that cutoff, where we're saying, okay, this is a rock texture, but we're also sufficiently close to just being it where we're just normally a land texture pixel, then we'll go ahead and apply this fall off, where we're mixing between the land pixel, what its normal land pixel would look like, versus its rock texture. So we're kind of mixing between the two colors so that it's a little smoother in transitioning between that rock cutoff line and the land texture cutoff. So that's all being done there. And again, if you remember with color linear interpolation, it's important that we're restricting these ranges so that the g-val 3 is a maximum of 1 or a minimum of a 0. So that's kind of important when I've constructed all of these cubic functions, that they're working on appropriately on the given range that we're looking for, cutoff range, and producing the desired minimum and maximum y's, which is 0 to 1. So that's why I did the cubic function. I cut off the way that we did. You could, use some sort of linear routine where you went from 0, 0 to point, whatever the line is, going from 0 to 0 to like 0.3, 1, whatever the line that's described by that would be the linear form of that, the linear computation, as opposed to a cubic function computation in this case. And they might look very kind of like one and the same, like you wouldn't be able to tell the difference. I just happened to implement it with this cubic function fall off. So going down a little bit further, that's kind of the next important point. We do a Heightmap, height mountain feathering. And what that means is that for any land pixel that's sufficiently close to the mountain cutoff range, what we're doing is we're color mixing between that land, what its land value would be, color value would be, versus the mountain color value that might exist if it was a mountain pixel. So that's very important, kind of paying attention to that, because that's how you feather smooth between the colors on like the height cutoff range. And similar, we do the same thing between all land pixels that are sufficiently close to the flood cutoff range, when their distance is given such that the ratio between the minimum maximum flood stage versus the distance between that height pixel and its flood stage is less than 0.1. If that ratio is true, then we'll go ahead and feather smooth, color mix, feather smooth those pixels as is. So, and then color mixing procedures are virtually the same as repeated throughout. So you can get into pretty complex regimens, if I'd imagine, just setting all of these up as desired. If you work with blenders like node system, color mixing node system, it's pretty much one and the same. Whenever you set up, like on the graphical GUI, you're setting up a color mixer, you're doing the same thing, potentially or likely, that is when you're adding one of these color interpolation lines. So that's kind of something cool to keep in mind that that each time we're adding that, we're doing that. So it can, in terms of the code, can resemble kind of like this node type structure. I mean, you can imagine it resembling pretty much being kind of very similar, one and the same. Although we do have some interesting and cool differences in that we can apply different types of textures without necessarily, we're not procedurally splatting textures, pre-created textures, but in essence, maybe it is kind of like that. In any event, going down a little bit further in the program, we have this new color. It's set to RGB. This is just kind of like some additional testing work. I go ahead and translate this new color so that it's applied to a 3-value tuple, because I believe that the new color was set up normally as a list object. You could probably just do a list list function or parentheses on the new color to do that, but I chose to do it this other way. And so this is assigned to the color map hash map or dictionary in Python, and that's written out to a given file. So once we've done that, that is then ready to go in terms of being sent to the bitmap2.py program, which actually goes about the process of creating the bitmap file, as opposed to just having this text all written in a kind of a string object that's not, like a photo file that's ready, or picture, like a GIF or a JPEG or anything like that, or a raw format photo type file. But in any event, that covers the basis of this tutorial, and I want to thank you for listening in and having the patience to listen through this, hopefully all of this, and thank you again for listening in, and you have a great day there.